our project is comprehensive analysis of the report on traffic system simulation using differential agent based model. So our team number is 18, and our main task is to see how differential agent based model can work on a traffic system simulation. So let's move further to with the introduction to differential agent based model. So our which is used to enhance the traffic flow simulation with machine learning techniques. So our core focus is to simulate the traffic flow using differential agent based model and implement the DABM to achieve a realistic vehicle behavior through advanced modeling techniques. We are also going to analyze the interaction that two vehicles have during their path on the road, and also we are going to do some groundwork. So project overview and objective. So first we our main objective is to understand the DABM implementation, in which we have modeled the vehicle behavior including speed regulation and lane changing dynamics. Then we have also explored the differential function that we have investigated few differential functions and enhanced the accuracy of our traffic simulation, that which kind of differential equations and function works best for our simulation. And also we have also considered future optimization case, in which we have studied the interaction of vehicles with any kind of intersection that happens on the road or the traffic light which is there on the road. So to understand how DABM works, we need to find a way that how we can measure the working of DABM with the working of any other algorithm. So what we have done, that we compare the working of DABM with the hard coding algorithm of a traffic simulation. In hard coding means that we have just coded an if else statement to see how two vehicles can interact in a real world situation. So our finding was that DABM approach resulted in smoother transition and more realistic traffic behavior than hard coded rules. Second, hard coded traffic rules, like we have just initialized the simulation using rigid definition of traffic behavior, leading to inflexible vehicle interaction, that if two vehicles are interacting, then in DABM they were interacting in a smoother way, whereas in hard coding method they were just interacting at a very small period of time. And we can also see that the complexity increases when we move from the hard coding to DABM, because the real world situation was complex to implement. And DABM approach in DABM approach, the vehicle interacts dynamically via differential function, allowing for the continuous state update based on their behaviors that each vehicle have. So each vehicles have their individual behavior which follows the DABM approach while their interaction with other vehicles on the road. So our vehicle agent that is being used in DABM framework has few learnable parameters, few constant parameters, and few interaction parameters. So learnable parameters include position, speed, and acceleration. Position means what will be the position of that vehicle at a given time on the road. Second, the speed of that vehicle on a given time on the road, and at that time the acceleration. For example, if the vehicle is near to another vehicle, the acceleration should be negative, or if it is far from or there is a lot of empty space, then it should accelerate in order to save time. Then the position and speed will also change based on the acceleration. Second is the dynamic interaction, that how the vehicle is interacting with the intersection or other vehicles or traffic, and also the traffic lights. Third is implementation of lane change. Lane change implementation is important because when two vehicles move on a road, another vehicle can overtake the first vehicle by changing their lane. So that kind of simulation is also being tested using DABM and the hard coding method to see how these two vehicles interact with each others. So, in traffic simulation environment design, there were three main features. First was the road environment, that a multi-lane circular road and a rectangular road was used to with realistic intersection and speed limit to simulate real traffic scenario. For example, we have created a rectangular road with four or five different lanes, and each lane have their own speed limit. In this way we can mimic a real world situation. Moreover, if a vehicle moves from one lane to another, it follows the speed limit of that lane. Second is traffic signal logic. We have also implemented the traffic signal logic with green, red and yellow, implementing a proper time period for all these threes. Third is vehicle interaction. During a vehicle interaction on the intersection means a T cross or a plus cross shape arise, and how will one vehicle will interact to other on that cases. On a empty road, on a straight road, the vehicle will move faster, but on the intersection it should slow down. That is also being learned by our DABM model. So, analysis of traffic flow without optimization. So, what was the main motive that the data analysis which we perform without optimization, that model generates a crucial data on travel time, vehicle density and cognitive pattern with a vital for the future optimization. Third is behavior analysis, that how the vehicle interact with each other and traffic signals, which helps in providing the deeper understanding of traffic patterns. And further, we have also seen that there are future possibilities or future research also can be done on traffic implementation or traffic optimization using DABMs. So here is a comparison between hard-coded versus DABM. The hard-coded follows the strict adherence to predefined rule, and DABM shows the smoother smooth adjustment. And also, there are other things like hard-code model was not effective to manage the traffic flow, whereas DABM was in more realistic and also sees what other things are there during the vehicle's interaction. So these are the following few key enhancements which can be done in our model. Uh, to improve the realism and functionality of traffic simulation. Let's move to the code portion, that how the code is being implemented. Here you can see that this is the hard coded portion, that how the hard coding part is done. In this you can see that we have initialized the road which is just zeros, array of zero. Then we have vehicles which have features like which lane it will first. Second is the speed, second is the speed, and third is the acceleration of that vehicle. For the another variable is color. So in this is the function which updates the position of a vehicle on a given time. It will just add the uh, it will just the it will just add the speed of that into the current position at every time frame. And this is a function which helps in visualizing the road. So here you can see how it is plotting the different plots of a time frame of 5 seconds. Like this is how the vehicles are moving. Here you can see the purple one is also moving, and all other vehicles are moving, and how they will interact with each other. For example, if one vehicles come in front of other, it will stop, it will not cross over it. So that is how the hard code algorithm is working. It is also checking that whether the car is passing or not. So here is one part. Visualizing this through plots is quite difficult, so we have just created the GIF or animated GIF for this. In this you can see how these vehicles are interacting. This is a better way to see how the DABM works in real world traffic scenarios. So currently this is a hard coded version, that all the vehicles are following a strict rules and they are just following that. There is no any kind of backtracking algorithm working in the on the back end of this. Moving further, we have implemented other things like road length and car length also was implemented, in which the position was seen that the one vehicle should not overtake a another move to the another lane if there is not enough distance, and these things were also measured. Second, here you can see that behavior, that these black lines are the length of the vehicle and the lane change is happening here. So moving further, let's move to the lane change logic, that how the lane change is happening. In lane change in hard code, what we see that whether the left or right side of any of lane is empty or not, then the vehicle will move to that lane. That is just a simple logic or a first logic that comes to a person, and that has been hard coded here. In this animation you can see how the vehicle will overtake each other. Here you can see the lane change that happened, or at any other place the lane change happens. So it's just a hard coded method that how the lane change will happen. It will just check that if the left or right side of the current lane is empty or not, and it will just move. Moving further, we have also added a traffic signal. So at traffic signal, the car will stop and it will remain stop until until the traffic signal get green. So we have also created a GIF for that. So here you can see currently the line gets red, so car stop, then green, the car starts to move again. In this way we have implemented a hard coded algorithm for the traffic simulation on all the three cases, that is normal road, where a road with any kind, a road with lane change cases, and also a traffic light cases. Here you can see the lane change also happens here, that if two vehicles come, it will move to the any side which is empty. So this is the hard coded portion. Let's move to the DBM, differential equation form. So here we have used PyTorch to simulate this environment, this situation, that how we are going to implement DABM models using PyTorch. So first we have created a vehicle agent. The vehicle agent will have following properties: position, speed, lane, size, length, and acceleration. Position, speed, and acceleration are parameters which can be learned, and lane, size, and length are fixed parameters, or a property of a vehicle that it will get. Then we have created an environment, road environment, which has road length, number of lanes, intersections, that how many T shape or plus shape intersections it will have, and a speed limit of each lane. So speed limit sorry, speed limit is an array or a vector which contains the speed limit of each individual lane. Say if there is a 5 lane, then speed limit will be an array of 5 values. So here we have compute loss. So in order to compute loss in DABM model, we have implemented three types of loss function. First is travel time loss, that is the vehicle is able to save time by accelerating or deaccelerating at right time. Second is congestion loss, that not too much vehicles are congested on a one lane. And third is collision loss. Collision loss is a kind of loss that happens or that triggers when the two cars get too much close to each other, and in this way the loss function will increase, and that will tell the model that no, you need to reduce the collision loss. So here you can see the travel time loss need to be reduced, that if the travel time is too much, the loss function will too high. Cognition loss will also less, and travel and collision loss is also less. So our total loss is just sum of all these three. Now this function simulates the all thing. Okay, so moving further, here we have created a road environment with a length of 300, number of lanes 3, intersection at 30. Like if the length is 300, then at 0 to 30 means at 30 there will be at intersection, and at intersection the speed of the cars would get less. Then these are the array of vehicle agents. As you can see, that number of vehicles is being defined here. We have 10. So 10 different vehicle agents is being created and stored in this array. Then we have used ADAM optimizer with a learning rate of 0.01, and this is the simulation equation that the PyTorch is running, the backtracking is happening. So here these are the 1000 iterations that has been happened and trained by the model. So here you can see how at step 1 this is the information about the vehicle 1, vehicle 2, vehicle 3, vehicle 4. In this way vehicle 10, and vehicle 1 is at lane 0 at position this with speed, and the length is that 4.50. In this way this all steps happen, and in this way the 1000 step has happened and the model has learned. So in also we have created a simulation in this, which you can see here, that how the two models or how the two vehicles will interact. So here you will see that currently there is no lane change in this, no lane change had happened. Is just that how two vehicles will interact, that if the distance get too less, it will slow down the vehicle. So here you can see that the two vehicles are not, one is not like colliding to each other, it is just too near to it. And here also the distance when get too close, the vehicle deaccelerates. Now moving further, lane change, that how the vehicle will lane change. So I have implemented the logic for the lane change, that how in which condition the lane change will happen. So there is a function of front distance, and front distance measures how much distance is left. On that basis the distance it decides in which way it needs to move. So here is also road environment with is intersection, that is there any intersection available or not. Then the compute loss has all the same functions as previous, and then we run the simulation. So in this you can see how a vehicle will change lane on the basis of whether the next lane is empty or not. So here you can see multiple vehicles are changing lane based on uh, how much time they can reduce or how much kind of optimization they can done, and each vehicle have their individual properties. So in this way we have trained this model also, and as you have seen, this is the animation or GIF of our lane simulation, lane changing simulation in traffic flow. Moving further, we have also implemented a traffic light and intersection also. So in this you can see that the road is there with traffic light position, intersection position at 50, and traffic light is at 150, and then vehicle again with the number of vehicle defined previously. And we have trained this model also, so all the models, all the agents are trained in that environment for 1,000 times. So again we have make a GIF of it, so it will be easy for us to visualize. And in this way you can see the light when green, the car is passing, but at the intersection is at 50, so the vehicle is stopping there or slowing down there. Okay, so you can see that, and the light also determines that vehicle will stop here or not. So the more training happens, the more model learns that where to perform what decision. Okay, so as you have seen, these are all the working of our team. And at the end, like, we have also improved the realism and functionality in traffic simulation, which help us to visualize how DABM models can be used in such kind of large population model, where each individuals have their own property and each of them work individually but interacts in any kind of given environments. So these are few future direction that can be happened, that we can enhance the realism by applying multiple lanes and multiple cross sections, intersections with real time vehicles entering from the intersection. And we can also optimize this by adding other kind of optimization models also. Thank you.